So far we have studied rectilinear motion with uniform acceleration, which we could apply to bodies moving vertically up or down under gravity. And we have also studied the principle of superposition of motion, which allows us to break complex motions into two parts, vertical and horizontal, analyze them separately, and then combine the results to get the net effect. We are going to use these two ideas here to get one important motion called projectile motion. And finally, we will be applying that motion to see how we can launch satellites around the Earth. Let us start with a simple motion, that of a body thrown vertically upward. So under the influence of gravity, it slows down, stops, and comes back again. And it slows down, stops, and accelerates back. Now, if we superpose a horizontal motion on this by giving it a sideways nudge, then this will become quite interesting. And that is precisely what cannons do. They launch the cannonball at an angle, thereby giving two components of motion, the vertical component, which will be governed by gravity, and the horizontal component, which will just keep moving it uniformly. So let's have a cannon here. And these are the two velocity components. The v cos theta component is horizontal, where theta is the angle of launch, and v sin theta will be the vertical velocity. We are going to tilt our cannon to some angle. Let us make it say 70 degrees. Now it is going at an angle. Here the horizontal motion is uniform, dependent on t, while the vertical motion is accelerated, dependent on t square. Such set of equations form a parametric equation of a parabola. And this is how it looks. So this is the path followed by our cannonball. Interestingly, what we achieved by launching it at 70 degrees could also be done by launching it at 20 degrees. Let us see how. So we will change it to 20 and launch again. So it lands at the same place. And this is true for all angles adding up to 90 degrees. We can try for another pair of values, say 30 degrees. It comes here. And for 60 degrees, it will also come at the same place. So it will have the same horizontal distance covered, which is called as the range. The next question is, then how can we maximize this range? What is the launch angle? Well, when the two are equal. So at 45 that happens, and which gives us the maximum range. And this is the trajectory for it. There are a couple of additional parameters which also influence the range. To understand them, we are going to keep the launching angle 0, so it will be squeezed out of the picture, and we are going to look at the trajectory here. So we have taken our cannon, we'll be launching it horizontally with the velocity of 25 units, and we have taken it to a height of 30 units, and this curve here is the trajectory that it followed. Let us see what happens to this trajectory. If we reduce the height, you will see the trajectory shrinks, and so does the range. If we increase the launching velocity, then you will see the trajectory changing the shape, giving us a greater range. So these two parameters, the height from which we are launching our projectile and the velocity with which we are launching our projectile, can increase the range. In the next part, we will consider projectiles whose range is so large that the curvature of the Earth needs to be taken into account.